This work addresses the Army's need to develop structural systems that are strong, tough, lightweight, energy dissipative, and can be used to protect soldiers. We have identified a unique biological model, which is the nose or the rostrum of the paddlefish, where a lattice-like architecture with complex geometry appears to give the rostrum its unique strength and resilience. And we believe that a fundamental understanding of how this lattice-like structure functions has the potential to provide novel insights into a wide range of disciplines. The beauty of this project is we have different labs in URDEC collaborating together to work towards one common goal, which is building better, safer, protective structures.
Having been deployed to Afghanistan and Iraq, I can tell you that one of the most important things we do is protect our soldiers and protect our equipment and protect our facilities. This has fantastic applications to build protective materials that can be easily put together, used in protection, and then taken apart and moved. I think this could actually be used in other applications in civil engineering as well. Maybe we can use this to help us build a better bridge or build a better structure. Maybe we can use this to build better walls. So I think this has a lot of applications beyond just protective structures.
So one of the really interesting areas that we're hoping this might go, and in fact, Rena's already got some computational modeling that suggests it may have benefits, is that the mesh network seems to function somewhat like a catcher's mitt, in the sense that when she's taking a simulation of a bullet going into metal using this mesh network, she finds that it distributes the stress quite a bit across the rostrum, thereby stretching it a lot more before it breaks when in comparison to just flat metal. So this can have some really interesting value if we're trying to make panels or other protective structures, where it may be much more resilient to having blasts or other penetrating objects trying to go through it.
So this research has 4 different components to it. In the first stage of the research, we are building the 3D geometry of the rostrum to be used as models for our computational mechanics simulations. And once we conduct the computational mechanics simulations, we are running advanced mathematical algorithm to gain insight into the failure mechanisms of this resilient biostructures. And to validate the theoretical prediction, we are conducting experiments on the nose of the paddlefish. We are doing the 3- and 4-point bending experiments on the paddlefish nose in the first stage of the experimental process. And in stage 2, we will be measuring the performance of the rostrum in its natural habitat. For this part of the research, we will be putting the paddlefish in swimming tanks to measure its performance.
This team involves electrical engineers, theoretical mathematicians, structural engineers, and biologists. And I think that really is what makes the approach new.
This is just at a small scale. So once we understand the geometrical characteristics, we already understand the properties, then this will be a scale up to a size of a wall or size of a building or a roof. That then we can, use similar geometrical characteristics to protect those structures.
So the really fun thing about this project is it's really brought together people who knew nothing about what the other people did. So it actually began through a fish biologist, and then we started meeting with mechanical engineers and having to explain what the biology was, what the nose was, and what it was composed of. The engineers had to explain what their goals were and what they could do. So we had this very fascinating mix between disciplines where everyone didn't know what each other was talking about, and they had to understand each other's language. And through doing that, they were able to inspire each other to do different things that they have been doing before and start making some of these discoveries. And I think this is really indicative of many of the really interesting problem areas in URDEC, where we're looking at the interface between different disciplines, whether it's engineering and biology or mechanics and environmental properties of different materials. There's a lot of very interesting interactions that you can look at when you bring different disciplines together.
I truly believe that this research work is a personification of one URDEC, one team.